Okay, so let's talk about our complexes and the coordination number. So remember, coordination number is the same thing as secondary valence. It's the number of ligands that are bonded to our transition metal. And what we find is that our coordination numbers will typically be 2, 4, or 6. So 2, that means my geometry is linear. And our primary example would be silver iron complexes. We saw that with the silver and ammonia ion complex. More commonly, we'll see 4 and 6. Now, if I have 4 ligands on my metal ion, it can either be square planar or tetrahedral. So just so you know, platinum 2 complexes will tend to be square planar. They do not occur as tetrahedral. Okay. Cobalt 3 and chromium 3, those always occur with a coordination number of 6. Okay, so platinum 2 always with coordination number of 4, and geometry is always square planar. Cobalt 3, chromium 3, always 6 and always octahedral. So, what about most metals? Well, most metals, depending upon your ligand, okay, can have a coordination number of 4 or 6. So, for example, my iron tetrachloride here, okay, that has 4 ligands, so, and it's tetrahedral. Whereas if I have a hexafluoride complex ion to my iron, it is octahedral and I can have 6 ligands. So what helps to determine this? Okay, and it's not so easy to predict. You should know these guys: platinum 2, silver, cobalt 3, chromium 3, and just be aware what are the factors that occur that will affect the number of ligands that you can have. And it's the size of the ligand. So fluoride is much smaller than chloride. So because the size is so much smaller, I can actually coordinate more fluorides than I can with the chlorides. And also the charge of the ligand. Okay, so let me give you an example for the charge. If I take something like nickel, I can either have 6 ammonia molecules, which gives me nickel NH3, 6, 2 plus, or only 4 cyanide ions. So why the difference? Because ammonia is neutral. So when I'm actually trying to put ammonia onto nickel, I can continue to put more on because I don't lose that positive charge. So you still have some attraction. Here with only 4, as I put my cyanide, so remember it's a nickel 2 plus. So as I add in and bond to my cyanide, I'm decreasing that charge on the complex. So here's a 2 minus. I have another cyanide come in to a 2 minus, they're going to repel each other because they are like charges. So charge actually has an impact on our coordination. Okay, so just so you're aware of that, and when you have the coordination number of 4, then unless it's platinum 2 complexes, you can't predict ahead of time if it's going to be tetrahedral or square planar, and that's something that we have to determine actually experimentally. Okay, so let's take a few minutes and let's talk about some common ligands. Okay, so when we talk about some common ligands, we can also say monodentates, okay, bidentate, and polydentate ligands. Okay, and what this means is that in your ligand you have a donor atom. And typically this will have the lone pair which bonds to your transition metal. So like in water, well, water actually consists of 3 atoms to make it. See, oxygen with the lone pair, that's my donor atom. Okay, and sometimes you might have a ligand that has 2 donor atoms, and we can talk about those 2 examples later. When we talk about monodentate ligands, bidentate, or polydentate, this means teeth. So this tells you in your ligand how many donor atoms you have. Okay, so this is 1 tooth, has 2 teeth, which means 2 donor atoms has more than 2. Okay, and when we're looking at the bidentate and polydentate ligands, you'll hear a term called chelator or chelating agents. Okay. And the reason that we use the term chelating agents is once my ion is bound to a chelating agent, it's very difficult to remove it from that chelating agent. And we actually use this at times to help clear a body of heavy metal toxins. Okay, like when we have lead poisoning and we know that there's free lead in the system, we can actually use EDTA to help chelate to the lead ion, and that allows us to extract it out through the kidneys instead of the lead ion continuing to cause problems. Okay, so let's give you an example of monodentate ligands. So common monodentate ligands. Okay, we already showed you water. And my donor atom is right here. Ammonia. And again, nitrogen is going to be my donor atom. Fluoride ion. We saw that with our nickel complex. Chloride ion. Okay. Cyanide. Okay. And that's going to be my donor. All right. And the thiocyanate. Okay, so just put minus sign. All right. So what happens? So what happens here is either one can act as a donor atom. More commonly the sulfur, but here's the thing. When you have either one, once it's bound, it's not going to rotate around. But where it's bound, this is a situation where either the nitrogen will go in and bind to the metal, or the sulfur will bind to the metal. Okay. We also have something like hydroxide, and we saw that when we basically looked at metals and how they're acidic. Okay, and we have the nitrite ion. Let me just put that in here. And here, again, it's either the nitrogen can act as a donor or the oxygen. More commonly, you'll see the oxygen act as the, let me double check, nitrite or nitro. I think more commonly you'll see the nitrogen act as a donor, but you'll see the oxygen as well. Okay, so either N or O can act as donor. Okay, now be aware, are there other ligands? Absolutely. You can have carbon monoxide. Okay. Can act as a ligand. Okay, and that too is a monodentate ligand, and it's typically the carbon that's going to act as the donor atom. Okay, so let's give you some examples of bidentates and polydentates, but I'll give you most of the bidentates that are in the textbook that I think you should know, and for the polydentates I'll give you just two that I think are important to know. Okay, so for the bidentate, it means it has two donor ligands that can be used at the same time. Okay, so this one both nitrogens. Okay, this is ethylene, diamine, and we abbreviate it as EN. Okay? You also have something like bipyridine. Okay, this is like BPY. Okay, now all of these that you see here at the intersections of lines, these are carbons. Okay, and what you'll find is that to make them neutral, no formal charge, you're going to add implied hydrogens. Okay, so carbon has the ability to have 4 bonds, so let me just redraw this so you can see it. This one has 4 bonds. This hydrogen, this carbon actually has a hydrogen to it. Okay, so we're implying the hydrogens when we draw this. We're not explicitly drawing it out. You can see it gets a little more messy. And I'm not even explicitly drawing out the carbons. Okay, so these are carbons. That's a carbon. And then you can see the number of hydrogens that go around the ring. So this is basically BPY, bipyridine. Okay. The other two I want to show you. This is the oxalate ion. Okay. Now, why the oxalate ion? Because remember, with the oxalate ion, this chelates actually calcium really well. Okay. So when you talk about oxalic acid and kidney stones, what we're talking about is that the oxalate will chelate out the calcium ion, and then that basically precipitates out in your kidneys, and that's how you get these small, tiny stones, the kidney stones, that are obviously very, very painful when you have to pass them. And finally, your carbonate. Right? Oh, let me just add my minus signs there. Okay, so this is the bidentate ligand. Okay? Alright, let's talk about polydentate ligands next, and then let's draw you a structure. Okay? So polydentate ligands go a little like this. Okay? They have definitely more than 2. So let me give you polydentate ligands. Okay, one of them is diethylene triamine. And this one has nitrogen with its lone pair. It has 2 carbon. This is my second donor atom. Then I have my 2 carbons. And then here's my third donor atom. So this has, basically, this is a tridentate. It's like 3 teeth to it. Another one is going to be triphosphate. And if you look at triphosphate ion, it looks like this. Okay, so in this case, for triphosphate, I have 1, 2, 3, 4, I have 5 donor ligands in triphosphate. And the last one that I'm going to show you that you'll really like, I think, it's called ethylene EDT, ethylene diamine tetraacetate. Okay, so, and we've used EDTA when we did our reaction rate, the chemical reaction rate experiment. And the reason this is so, we used it, is because it has 6, actually, donor atoms, ethylene diamine tetraacetate. And so it basically completely sequesters out our ions. And because we wanted our rate law not to be affected by any possible catalyst in our reaction mix, that's why we used a drop of EDTA. Like I mentioned earlier, if you have this in your system, some unwanted heavy metal ions, you can use EDTA. All right, so this looks like ethylene diamine, so tetraacetate. So here's 1. Here's 2. Okay. That's my third one. I have my 2 carbons in between. I have my 4th donor ligand. And finally, 5, 6. So this will completely wrap around any metal ion that can accommodate coordination number 6. So 1, 2, 3, 4, 5, 6. So 6 donor atoms in EDTA. So let me just show you, let me just draw it out. Complex. So let's do a cobalt with 3 ethylene diamines. And this is a 3+. But here is my cobalt and ethylene diamine, I have 2 nitrogens, 2 carbons, right? So I'm going to do, here's my nitrogen. Put an H2 right here. Okay, so the lone pair of this nitrogen and the lone pair of this nitrogen will bond to my cobalt 3. Okay, again, I have 2 that bind. This way. Be aware it's the nitrogen that binds to my cobalt. Two. CH2, CH2. Sorry, I'm gonna make it look messy there. So this is basically the coordination sphere for my complex ion. Okay. Now, when we look at it, why is it called a chelating effect? Well, let's compare, okay, why polydentates and bidentates are so important. So if you look just at the formation of these complexes, okay, so if I take my nickel 2+, okay, so it's complex with the water, and I add aqueous ammonia to get my hexamine nickel 2+ complex. Okay, just so you know, the K formation, remember we were talking about formation complexes earlier? Okay, is 1.2 times 10 to the 9th. If you compare that to adding in your ethylene diamine, okay, I have a bidentate here. Because they both are bound at the same time, it's harder to pull the whole thing off. And that's really what we're talking about. Because it's so difficult to pull the whole thing off, because I have 2 of them attached versus just 1, you'll find that the Kf is 6.8 times 10 to the 17th. Okay? So, the binding, it binds 10 to the 8th times better than having a monodentate. Okay, so that's why bidentates and polydentates, our chelators, are so important. They're like a claw, and they just go in and they grab that ion and they don't let go of it. Okay, so and you can see just by looking at their equilibrium constants. Okay, so you can read up about your chelators in biological systems, which would include looking at heme, because that's a very important one. Cytochromes, okay, that's also very important. So we have a lot of transition metals in our body that we need, okay, and you're going to find that a lot of our proteins and peptides will chelate to